Imagine the fabric of the universe itself rippling like the surface of a pond, bending and stretching as two colossal black holes collide in the depths of space. This isn't science fiction, it's the reality of gravitational waves, the universe's most extreme cosmic messengers. These invisible ripples in space-time, predicted by Einstein over a century ago, carry secrets about the most violent and mysterious events in the cosmos. From colliding black holes to the explosive deaths of neutron stars, gravitational waves have opened a new window into the universe, allowing us to listen to the echoes of events billions of light years away. In this video, we'll uncover 30 astonishing facts about these extreme gravitational waves, facts that will challenge what you thought you knew about space, time, and the very nature of reality. So buckle up, because we're about to dive into the cosmic symphony of the universe's most extreme phenomena. Stay tuned, because by the end of this journey, you'll see the universe in a whole new way. Now, let's step into a moment that changed our understanding of the universe forever. In September 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves for the very first time. This groundbreaking discovery confirmed a prediction Albert Einstein made a century earlier, proving that spacetime itself could ripple like waves on a pond. The source of these waves, two black holes, each about 30 times the mass of our Sun, spiraling toward each other and merging in a cataclysmic collision over 1 billion light-years away. The energy released in that single event was so immense that, for a fraction of a second, it outshone all the stars in the observable universe combined. This detection didn't just validate Einstein's theory of general relativity. It opened an entirely new way for us to explore the cosmos. For the first time, we could listen to the universe, hearing the echoes of events that were previously invisible to us. This marked the dawn of gravitational wave astronomy, a field that continues to reveal the universe's most extreme and mysterious phenomena. And this was just the beginning. Stay tuned, because the discoveries that followed are even more astonishing. Now let's dive into the very fabric of the universe itself. Gravitational waves are ripples in space-time, the invisible fabric that makes up everything we know. Imagine space-time as the surface of a calm pond. When you drop a pebble into the water, it creates ripples that spread outward in all directions. In the same way, when massive cosmic events occur, like black holes colliding or neutron stars merging, they send ripples through space-time itself. These ripples are what we call gravitational waves, but here's the mind-blowing part. Space-time isn't just an abstract idea, it's the stage on which the entire universe plays out. When these waves pass through, they stretch and squeeze space-time, warping the distances between objects. Think of it like a cosmic trampoline. If you were standing on it, you'd feel yourself being pulled and pushed as the waves rolled by. These waves carry information about the most violent and energetic events in the universe, giving us a whole new way to see what's happening out there. And just like the ripples in a pond, they travel outward, carrying the story of their origins across the cosmos. This ripple effect isn't just a cool analogy. It's a fundamental way the universe communicates with us, revealing secrets that light alone could never show. Now, let's shift our focus to something truly extraordinary: the speed of gravitational waves. These ripples in space-time don't just travel, they race across the universe at the speed of light. That's right, gravitational waves move at the fastest speed possible, making them the ultimate cosmic messengers. To put it into perspective, if you could hitch a ride on one of these waves, you'd be traveling at about 186,000 miles per second. That's fast enough to circle the Earth 7.5 times in just 1 second. But why does this matter? Well, this incredible speed means that when a massive event like a black hole collision happens, the gravitational waves it produces reach us almost instantly. This allows scientists to observe these events in real time, giving them a front-row seat to some of the most dramatic moments in the universe. Imagine being able to witness the birth of a black hole or the collision of neutron stars as it happens, billions of light years away. It's like having a live broadcast from the farthest reaches of space. This real-time observation isn't just exciting, it's revolutionary. It opens up new possibilities for understanding the universe, from tracking the movements of massive objects to testing the limits of Einstein's theory of relativity. So, the next time you hear about gravitational waves, remember, they're not just ripples in space-time, they're the universe's fastest, most powerful messengers, bringing us news from the farthest corners of existence. Now, let's turn our attention to one of the most groundbreaking moments in gravitational wave astronomy, the detection of the loudest gravitational wave ever recorded. In August of 2017, scientists made history when they observed the collision of two neutron stars, an event so powerful it sent ripples through space-time and lit up the cosmos with a burst of light. This wasn't just any cosmic event, it was the first time gravitational waves and electromagnetic radiation, like light, were detected from the same source. The collision, located 130 million light-years away, was so intense that it produced a gamma-ray burst, a flash of light so bright it could be seen across the universe. But the real treasure trove came from the aftermath. As the neutron stars merged, they spewed out a glowing cloud of heavy elements like gold, platinum, and uranium. This confirmed a long-standing theory that neutron star collisions are cosmic factories for creating the heaviest elements in the universe. Before this discovery, scientists weren't entirely sure where elements like gold came from. Now, we know that these dazzling cosmic crashes are responsible for forging the precious metals we find on Earth. The data from this event didn't just solve a mystery, it opened up a new way to study the universe. By combining gravitational wave observations with traditional telescopes, scientists gained a richer, more complete picture of what happens during these extreme events. It's like having both sound and visuals for the first time, giving us a front-row seat to the universe's most spectacular shows. This discovery wasn't just a milestone for science, it was a reminder of how interconnected the cosmos truly is, and how much we still have to learn from its most extreme phenomena. Now, shifting our focus to the titanic forces at play in the cosmos, let's dive into the incredible power of black hole mergers. When two black holes spiral toward each other, locked in a cosmic dance, they create some of the most extreme gravitational waves ever detected. These events are not just powerful, they're mind-bogglingly energetic. In fact, the energy released during a black hole merger can outshine the combined light of every star in the observable universe, if only for a brief moment. Imagine the sheer scale of that. Two invisible objects, each with masses tens or even hundreds of times greater than our Sun, colliding and unleashing a torrent of energy that ripples across spacetime itself. What makes these mergers so extraordinary is the way they distort the fabric of the universe. As the black holes orbit each other, they stretch and squeeze spacetime, sending out gravitational waves that carry away energy. The closer they get, the faster they spin, until they finally collide in a cataclysmic explosion of energy. This energy isn't just a faint whisper, it's a deafening roar in the language of the cosmos, detectable billions of light years away. But here's the fascinating part. Despite the immense energy released, black hole mergers don't produce any light. Unlike neutron star collisions, which light up the sky with gamma-ray bursts and glowing clouds of heavy elements, black hole mergers are entirely dark. They're invisible to traditional telescopes, making gravitational waves our only window into these extreme events. This is why instruments like LIGO and Virgo are so crucial. They allow us to hear the universe in a way we never could before, revealing the hidden symphonies of black holes colliding in the void. These mergers aren't just awe-inspiring, they're also key to understanding the universe's most mysterious objects. By studying the gravitational waves they produce, scientists can learn about the masses, spins, and even the origins of black holes. Each merger is like a cosmic fingerprint, offering clues about how these enigmatic objects form and evolve. And as we detect more of these events, we're piecing together a clearer picture of the universe's most extreme phenomena, one ripple at a time. With that in mind, let's turn our attention to another fascinating player in the gravitational wave symphony, neutron stars, and the crucial role they play in shaping our understanding of the cosmos. Now, let's explore the fascinating role of neutron stars in the cosmic symphony of gravitational waves. Unlike black holes, neutron stars are the incredibly dense remnants of massive stars that have exploded in supernova. Packing the mass of 1.5 times our Sun into a sphere no larger than a city, these objects are so dense that a single teaspoon of neutron star material would weigh billions of tons. When two neutron stars collide, the result is nothing short of spectacular, a cosmic event that not only generates gravitational waves but also lights up the universe in a dazzling display of light and energy. Neutron-star collisions are unique because they produce both gravitational waves and electromagnetic radiation, making them visible to both gravitational wave detectors and traditional telescopes. This dual signature gives scientists an unprecedented opportunity to study these events in multiple ways. For instance, the historic detection of a neutron star merger in 2017 marked the first time astronomers observed both gravitational waves and light from the same event. This groundbreaking discovery provided a wealth of data, confirming theories about how heavy elements like gold and platinum are formed in the universe. But why are neutron star collisions so important? These events occur in some of the most extreme environments in the cosmos, where matter is subjected to unimaginable pressures and temperatures. By studying the gravitational waves they produce, scientists can learn about the internal structure of neutron stars, including how matter behaves under such extreme conditions. This information is crucial for understanding the fundamental laws of physics, particularly in regimes that cannot be replicated on Earth. Moreover, neutron star collisions are thought to be the birthplaces of many of the universe's heavy elements. When two neutron stars merge, they eject material rich in neutrons, which rapidly combines to form elements like gold, platinum, and uranium. This process, known as rapid neutron capture or the R process, is responsible for creating some of the most valuable and rare elements in the universe. In a very real sense, the gold in your jewelry or the uranium used in nuclear reactors may have originated from a neutron star collision billions of years ago. These collisions also provide a unique laboratory for testing Einstein's theory of general relativity. The intense gravitational fields and rapid motions involved in neutron star mergers push the boundaries of our understanding of spacetime. By comparing the gravitational waves and light emitted during these events, scientists can test whether general relativity holds true under such extreme conditions or if new physics is at play. In essence, neutron star collisions are cosmic treasure troves, offering insights into everything from the behavior of matter at its most extreme to the origins of the elements that make up our world. They remind us that the universe is not only vast and mysterious but also deeply interconnected, with each event contributing to the grand tapestry of cosmic history. With that in mind, let's turn our attention to another intriguing mystery of the cosmos, the enigmatic intermediate mass black holes and the gravitational waves they produce. Now let's venture into the shadowy realm of intermediate mass black holes, a cosmic puzzle that has long intrigued scientists. These elusive objects occupy a unique place in the universe, sitting between the smaller stellar mass black holes, formed from collapsing stars, and the colossal supermassive black holes that lurk at the centers of galaxies. Intermediate mass black holes are thought to weigh anywhere from a few hundred to a few 100,000 times the mass of our Sun, making them a fascinating missing link in the black hole family tree. The detection of gravitational waves from intermediate mass black holes has been a rare but groundbreaking achievement. Unlike their smaller or larger counterparts, these black holes are incredibly difficult to observe directly. They don't emit light, and their gravitational influence is often too subtle to detect unless they're actively feeding on nearby matter or merging with other objects. This is where gravitational wave astronomy comes in. By listening for the ripples in spacetime caused by their collisions, scientists have begun to uncover clues about these mysterious entities. One of the most exciting discoveries came in 2019, when the LIGO and Virgo observatories detected gravitational waves from what appeared to be the merger of two intermediate mass black holes. This event, known as GW190521, was a landmark moment in astrophysics. It not only provided the first strong evidence for the existence of intermediate mass black holes, but also offered a glimpse into how they might form and evolve. So, how do these enigmatic objects come into existence? One leading theory suggests that intermediate mass black holes could form through the gradual merging of smaller black holes in dense star clusters. Over time, these mergers could build up enough mass to create an intermediate mass black hole. Another possibility is that they are the remnants of the universe's earliest stars, which were much more massive than the stars we see today. These primordial black holes could have grown over billions of years, eventually reaching the intermediate mass range. The study of intermediate mass black holes also has profound implications for our understanding of galaxy formation. Some scientists believe they could serve as the seeds for supermassive black holes, growing over time by consuming gas, stars, and even other black holes. If this is true, intermediate mass black holes could hold the key to understanding how the universe's most massive structures came to be. Yet, despite these exciting possibilities, intermediate mass black holes remain shrouded in mystery. Their rarity and the challenges of detecting them mean that every new observation is a treasure trove of information. Each gravitational wave signal brings us closer to unraveling their secrets, from their origins to their role in the cosmic web. As we continue to explore the universe's most extreme phenomena, intermediate mass black holes remind us that there is still so much to discover. They challenge our understanding of black holes and push the boundaries of what we thought was possible. And with every new detection, we inch closer to solving one of the cosmos' greatest mysteries. With that, let's shift our focus to another fascinating aspect of gravitational waves: the distinctive chirp sound they produce, and how this unique signature helps scientists decode the secrets of the universe. Now, let's tune our ears to one of the most fascinating aspects of gravitational waves: their unmistakable chirp. This unique sound, detected by instruments like LIGO, is more than just a cosmic curiosity. It's a key that unlocks the secrets of the universe's most extreme events. When two massive objects, like black holes or neutron stars, spiral toward each other, they create ripples in spacetime that travel across the cosmos. As these objects get closer, their gravitational pull intensifies, causing the frequency of the waves to increase. This rapid rise in frequency produces a distinctive sound, a chirp, that scientists can detect and analyze. Imagine the sound of a bird's chirp, but sped up and amplified by the immense power of colliding cosmic giants. That's what gravitational waves sound like when they reach Earth. This chirp is incredibly valuable to researchers. By studying its characteristics, such as how quickly the frequency rises and how loud the chirp is, scientists can determine the masses of the objects involved, how far away they are, and even how they merge. For example, a short, sharp chirp might indicate the collision of two small black holes, while a longer, more drawn-out chirp could signal the merger of larger objects like neutron stars. It's like listening to a cosmic fingerprint where each chirp tells a unique story about the event that created it. The chirp also helps scientists pinpoint the source of the gravitational waves. By comparing the signals detected at different observatories around the world, researchers can triangulate the location of the event in the sky. This allows them to direct telescopes to the right spot, enabling them to observe the aftermath of the collision in other wavelengths of light, such as X-rays or gamma rays. In fact, the chirp from the neutron star collision detected in 2017 led to one of the most significant multi-messenger astronomy events in history, where gravitational waves and light were observed simultaneously. But the chirp isn't just a tool for scientists, it's also a way to bring the universe closer to us. By converting gravitational wave data into sound, researchers have made these cosmic events audible, allowing us to hear the universe in a whole new way. It's a reminder that the cosmos isn't just something we see, it's something we can listen to too. As we continue to explore the universe's most extreme phenomena, the chirp of gravitational waves serves as a powerful reminder of how much we can learn by listening. It's a sound that connects us to the distant reaches of space and time, offering a glimpse into the violent, beautiful, and mysterious events that shape our universe. With that, let's turn our attention to the cosmic dance of binary systems, where pairs of black holes or neutron stars spiral closer together, creating gravitational waves that echo across the cosmos. Now, let's step into the mesmerizing world of binary systems, where pairs of cosmic heavyweights, black holes or neutron stars, engage in a slow, spiraling dance that sends ripples through the fabric of spacetime. These systems are like celestial partners locked in a gravitational embrace, gradually losing energy as they orbit each other. Over time, their dance grows faster and tighter, culminating in a spectacular merger that sends out powerful gravitational waves. Imagine two black holes, each with masses tens or even hundreds of times greater than our Sun, circling one another in the vast emptiness of space. As they orbit, they emit gravitational waves which carry away energy and cause the pair to spiral closer together. This process can take millions or even billions of years, but as the distance between them shrinks, the intensity of the gravitational waves increases. The closer they get, the faster they spin, creating a crescendo of ripples that build until the final, explosive moment of collision. Neutron stars, the dense remnants of supernova explosions, also perform this cosmic dance. When two neutron stars orbit each other, their immense gravitational pull distorts spacetime, sending out waves that ripple across the universe. Unlike black holes, neutron star mergers often produce not just gravitational waves but also bursts of light, making them some of the most exciting events for astronomers to study. The collision of two neutron stars in 2017, for instance, not only produced gravitational waves but also a brilliant flash of light observed across multiple wavelengths, from gamma rays to visible light. What makes binary systems so fascinating is the sheer variety of outcomes they can produce. Depending on the masses and types of objects involved, the merger can result in a more massive black hole, a neutron star, or even a black hole-neutron star hybrid. Each scenario leaves behind a unique signature in the gravitational waves, offering scientists a wealth of information about the nature of these extreme objects. The study of binary systems has also deepened our understanding of how the universe evolves. By observing the mergers of black holes and neutron stars, researchers can learn about the distribution of these objects across the cosmos, the rates at which they collide, and the role they play in shaping galaxies. It's like piecing together a cosmic puzzle where each merger provides a new clue about the universe's history and structure. As we continue to explore the universe's most extreme phenomena, the cosmic dance of binary systems reminds us of the dynamic and ever-changing nature of the cosmos. These events are not just fleeting moments of destruction, they are also moments of creation, forging new objects and reshaping the universe in ways we are only beginning to understand. With that, let's shift our focus to the challenges of detecting these elusive gravitational waves and the incredible technology that makes it possible. Now, let's turn our attention to the remarkable challenges scientists face when trying to detect these faint ripples in spacetime. Gravitational waves are incredibly subtle, stretching and squeezing spacetime by distances smaller than the width of an atom. To catch these elusive signals, researchers rely on some of the most sensitive instruments ever built, like the Laser Interferometer Gravitational Wave Observatory, or LIGO. But even with such advanced technology, the task is far from easy. One of the biggest hurdles is the sheer sensitivity required. LIGO detectors are designed to measure changes in distance thousands of times smaller than a proton. To put that into perspective, it's like trying to detect a change in the distance between the Earth and the Sun that's no more than the thickness of a human hair. This level of precision is mind-boggling, and it's only possible thanks to cutting-edge engineering and decades of innovation. But sensitivity isn't the only challenge. Earth itself can interfere with these delicate measurements. Everyday vibrations, from passing trucks to ocean waves crashing on distant shores, can create noise that masks the faint signals of gravitational waves. Even the tiniest seismic activity, like a small earthquake halfway across the globe, can disrupt the detectors. To combat this, LIGO and similar observatories are equipped with sophisticated systems to isolate the instruments from these disturbances. They use advanced suspension systems and vacuum chambers to shield the detectors from external noise, ensuring that only the ripples of spacetime are captured. Another issue is the sheer rarity of detectable events. While gravitational waves are constantly passing through Earth, only the most extreme cosmic events like black hole mergers or neutron star collisions produce waves strong enough to be detected. These events are rare, and even when they occur, the signals are fleeting, lasting only a fraction of a second. This means scientists must constantly monitor the detectors, sifting through mountains of data to find those precious moments when the universe whispers its secrets. Despite these challenges, the detection of gravitational waves has revolutionized our understanding of the cosmos. Each successful detection is a triumph of human ingenuity, a testament to our ability to overcome seemingly insurmountable obstacles in the pursuit of knowledge. And as technology continues to improve, the future of gravitational wave astronomy looks brighter than ever, promising even more extraordinary discoveries. With that in mind, let's explore what lies ahead for this groundbreaking field and the next generation of instruments that will push the boundaries of what we can observe. As we look to the horizon of gravitational wave astronomy, the future holds even more groundbreaking possibilities. One of the most exciting developments on the horizon is the Laser Interferometer Space Antenna, or LISA. Unlike ground-based observatories like LIGO, LISA will operate in space, free from the vibrations and noise that plague Earth-based detectors. This ambitious project, led by the European Space Agency in collaboration with NASA, will consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers. These spacecraft will use lasers to measure the tiniest distortions in spacetime caused by passing gravitational waves. LISA's unique position in space will allow it to detect waves at much lower frequencies than ground-based observatories can. This means it will be able to observe events that are currently beyond our reach, such as the mergers of supermassive black holes at the centers of galaxies. These colossal collisions, which can involve black holes billions of times more massive than our Sun, produce gravitational waves that ripple across the universe for millions of years. By capturing these signals, LISA will give us an unprecedented view into the formation and evolution of galaxies, shedding light on some of the universe's most profound mysteries. But LISA isn't the only project poised to revolutionize gravitational wave astronomy. Other upcoming missions, like the Einstein Telescope and Cosmic Explorer, aim to push the sensitivity of ground-based detectors even further. These next-generation observatories will be capable of detecting waves from events that are even more distant and extreme, potentially revealing new classes of cosmic phenomena. Imagine being able to observe the very first black holes that formed after the Big Bang, or catching the faint echoes of exotic objects like cosmic strings or wormholes. The possibilities are as vast as the universe itself. What makes these future projects so exciting is their potential to answer questions we haven't even thought to ask yet. Every time we've built a more sensitive detector, we've discovered something entirely unexpected, like the existence of intermediate mass black holes or the precise details of neutron star collisions. With LISA and its successors, we're not just expanding our ability to observe the universe, we're opening the door to entirely new realms of discovery. As we prepare for this next chapter in gravitational wave astronomy, one thing is certain: the universe still has countless secrets waiting to be uncovered. And with each new detection, we'll come one step closer to understanding the true nature of spacetime and the cosmic forces that shape it. So, as we marvel at the achievements of today, let's also look forward to the extraordinary revelations that tomorrow's observatories will bring. Now, let's turn our attention to one of the most awe-inspiring sources of gravitational waves: supermassive black holes. These colossal giants, often found at the very heart of galaxies, are millions or even billions of times more massive than our Sun. When two supermassive black holes spiral toward each other and eventually merge, they unleash gravitational waves of unimaginable power. These waves ripple through space-time, carrying energy equivalent to the combined mass of the merging black holes. It's a cosmic event so immense that it can shake the very fabric of the universe. But what makes these mergers so significant? For one, they play a crucial role in the formation and evolution of galaxies. When galaxies collide, their central supermassive black holes are drawn together, orbiting each other in a cosmic dance that can last for millions of years. As they get closer, they emit gravitational waves, losing energy and spiraling inward until they finally merge. This process not only shapes the structure of galaxies, but also influences the distribution of stars and gas within them. In a way, supermassive black holes are the architects of galactic evolution, sculpting the universe on the grandest scales. The detection of gravitational waves from supermassive black hole mergers could also help us answer some of the biggest questions in astrophysics. For instance, how do these black holes grow to such enormous sizes? What role do they play in the formation of the first galaxies? And how do their mergers affect the surrounding environment? By studying these waves, we can gain insights into the life cycles of galaxies and the forces that drive their growth and transformation. What's truly remarkable is that these mergers produce gravitational waves at frequencies that are too low for ground-based detectors like LIGO to pick up. That's where space-based observatories like LISA come in. With its ability to detect lower frequency waves, LISA will give us a front-row seat to the mergers of supermassive black holes, allowing us to witness these monumental events in unprecedented detail. It's like having a new set of eyes to explore the universe's most extreme phenomena. As we continue to unravel the mysteries of supermassive black holes, one thing becomes clear: these cosmic giants are not just fascinating in their own right, they are key to understanding the universe's grandest structures. Their mergers and the gravitational waves they produce offer us a unique window into the forces that have shaped the cosmos since its earliest days. And with each new discovery, we come closer to piecing together the story of how galaxies, including our own, came to be. Now, let's journey back to the very beginning of everything, the Big Bang. Imagine the universe as a newborn, bursting into existence in a fiery explosion of energy and matter. But what if we could hear the echoes of that moment, the faint whispers of gravitational waves rippling through spacetime from the dawn of time itself? This is the tantalizing possibility of detecting primordial gravitational waves, the oldest signals in the cosmos. These waves, if they exist, would carry the imprint of the universe's earliest moments, offering us a glimpse into the conditions that shaped everything we see today. They would be the ultimate time capsule, a direct link to the instant when the universe expanded faster than the speed of light during a period known as inflation. Detecting these waves would not only confirm this theory but also reveal the energy scales at which the universe began its rapid expansion. The challenge, of course, is that these primordial waves are incredibly faint, buried beneath the noise of more recent cosmic events. To find them, scientists are turning to specialized instruments like cosmic microwave background telescopes, which look for subtle patterns in the oldest light in the universe. These patterns, known as B-mode polarization, could be the telltale signature of gravitational waves from the Big Bang. If we succeed in detecting these ancient ripples, it would be a monumental breakthrough. We could answer fundamental questions about the universe's origins, such as what triggered the Big Bang and whether our universe is just one of many in a vast multiverse. It's like uncovering the first chapter of a cosmic story, one that has been hidden for billions of years. As we continue to search for these elusive waves, we're reminded of the incredible power of science to uncover the deepest mysteries of existence. The echoes of the Big Bang are out there waiting to be heard, and when we finally tune in, we'll be listening to the very heartbeat of the universe itself. Now let's shift our focus to the sheer power behind these cosmic ripples. Gravitational waves aren't just subtle whispers in the fabric of spacetime, they carry an astonishing amount of energy. In fact, during a merger of massive objects like black holes or neutron stars, the energy released in the form of gravitational waves can be equivalent to several times the mass of our Sun being converted into pure energy. To put that into perspective, imagine the Sun, our star, which powers life on Earth, being completely transformed into energy in an instant. That's the kind of mind-boggling power we're talking about. This energy isn't just theoretical. When LIGO detected the first gravitational waves in 2015, scientists calculated that the merging black holes released energy equivalent to about 3 solar masses. That's 3 times the mass of the Sun, converted into ripples that traveled across the universe for over 1 billion years before reaching us. It's a staggering reminder of how violent and energetic these cosmic events can be. But where does all this energy come from? During a merger, as 2 massive objects spiral closer and closer, they lose energy in the form of gravitational waves. This energy loss causes them to speed up, creating even stronger waves until they finally collide. The moment of collision is when the most energy is released, often in a fraction of a second. It's like a cosmic explosion, but instead of light and heat, the energy is carried away by these ripples in spacetime. What's even more fascinating is that this energy isn't lost. It travels across the universe, stretching and squeezing spacetime as it goes. And when it reaches us, it gives us a front row seat to some of the most extreme events in the cosmos. The energy of gravitational waves is a testament to the incredible forces at work in the universe, forces that shape galaxies, forge elements, and even help us understand the very fabric of reality. As we continue to detect these waves, we're not just observing distant events, we're measuring the energy that drives the universe itself. And with each new detection, we're reminded of just how dynamic and powerful the cosmos truly is. Now, let's take a closer look at how gravitational waves actually interact with the fabric of spacetime itself. When these waves travel through the universe, they don't just pass by unnoticed, they physically distort the shape of spacetime. Imagine spacetime as a vast, stretchy sheet. When a gravitational wave moves through it, the sheet doesn't stay flat. Instead, it stretches in one direction while squeezing in another, creating a ripple effect that warps the very structure of reality. This stretching and squeezing happens in a very specific way. As a gravitational wave passes through, it causes spacetime to oscillate in 2 perpendicular directions. Think of it like this: if you were standing in the path of a gravitational wave, you wouldn't feel anything, but you might notice that the space around you is subtly changing shape. Objects in one direction would appear to stretch apart, while in the perpendicular direction, they'd be squeezed closer together. It's as if the universe itself is breathing, expanding and contracting in a rhythmic dance. What's truly remarkable is that this distortion isn't just theoretical, it's measurable. Instruments like LIGO are designed to detect these tiny changes in spacetime. The detectors use laser beams to measure the distance between mirrors placed kilometers apart. When a gravitational wave passes through, it alters the distance between these mirrors by an almost unimaginably small amount, less than the width of a single proton. Yet, this minuscule change is enough to confirm the presence of a gravitational wave and reveal its source. This ability to distort spacetime is one of the most fascinating aspects of gravitational waves. It shows us that spacetime isn't just a static backdrop for the universe, it's a dynamic, flexible medium that can be bent, stretched, and squeezed by the most energetic events in the cosmos. And as we continue to study these waves, we're gaining a deeper understanding of how the universe works on the most fundamental level. Next, we'll explore how this distortion of spacetime connects to some of the most mysterious and extreme objects in the universe, black holes and neutron stars, and how their interactions create the gravitational waves we detect. Now, let's shift our focus to a fascinating intersection of physics, where gravitational waves meet the strange and mysterious world of quantum mechanics. While gravitational waves are a product of Einstein's theory of general relativity, which describes the universe on a large scale, quantum mechanics governs the behavior of the smallest particles in existence. At first glance, these two realms seem worlds apart, but in extreme cosmic events, they might just collide in ways we're only beginning to understand. One of the most intriguing possibilities is the detection of quantum gravity effects through gravitational waves. Quantum gravity is a theoretical framework that aims to unify general relativity with quantum mechanics, two pillars of modern physics that so far don't play nicely together. In extreme environments, like the moments just before a black hole merger or the violent collision of neutron stars, the fabric of spacetime is stretched and warped to its limits. It's in these extreme conditions that scientists believe quantum gravity might leave its marked tiny, subtle imprints that could be encoded in the gravitational waves produced by these events. Imagine this: as two black holes spiral closer and closer, the intense gravitational forces could cause spacetime to behave in ways that classical physics can't fully explain. At these scales, the smooth, continuous fabric of spacetime predicted by general relativity might break down, revealing a grainy quantum structure beneath. This is where quantum mechanics steps in, suggesting that spacetime itself might be made up of discrete, quantized units, like pixels on a cosmic screen. If this is true, gravitational waves could carry faint echoes of this quantum structure, offering us a glimpse into the fundamental nature of reality. Detecting these quantum effects, however, is no small feat. The signals would be incredibly faint, buried within the already subtle ripples of gravitational waves. But with next-generation detectors and advanced data analysis techniques, scientists are hopeful that they might one day uncover these quantum fingerprints. Such a discovery would revolutionize our understanding of the universe, bridging the gap between the very large and the very small. So, while we're still far from fully understanding the role of quantum mechanics in gravitational waves, the potential is immense. These ripples in spacetime might not just tell us about black holes and neutron stars, they could also hold the key to unlocking one of the greatest mysteries in physics: how gravity and quantum mechanics fit together in the grand tapestry of the cosmos. Next, we'll dive into how gravitational wave detections are revealing entirely new populations of black holes, challenging our existing theories and reshaping our understanding of the universe. Now, let's turn our attention to one of the most groundbreaking discoveries made possible by gravitational waves: the revelation of entirely new populations of black holes. Before the era of gravitational wave astronomy, our understanding of black holes was largely based on observations of their effects on surrounding matter or light. But with the ability to listen to the universe through gravitational waves, scientists have uncovered black holes that were previously hidden from view, reshaping our understanding of these enigmatic objects. One of the most surprising findings has been the detection of black holes with masses far larger than what traditional theories predicted. These so-called stellar mass black holes were thought to form from the collapse of massive stars, with typical masses ranging from about 5 to 20 times that of our Sun. However, gravitational wave detections have revealed black holes with masses upwards of 50, 60, or even 100 times the mass of the Sun. These discoveries have forced scientists to rethink how such massive black holes form and evolve. Could they be the result of multiple black holes merging over time, or do they form through entirely different processes that we're only beginning to understand? Equally fascinating is the discovery of black holes in binary systems that don't fit the expected patterns. For example, some detected pairs of black holes have wildly mismatched masses, with one being significantly larger than the other. This challenges the idea that black holes in binary systems form from stars of similar sizes. Instead, it suggests a more complex and dynamic process, possibly involving interactions in dense stellar environments like globular clusters, where black holes can pair up in unexpected ways. These discoveries aren't just adding to our catalog of black holes, they're forcing us to rewrite the rules. For decades, our understanding of black holes was based on a relatively narrow set of observations. But gravitational waves have opened a new window, revealing a universe far more diverse and unpredictable than we ever imagined. Each detection brings new questions. How do these massive black holes form? What environments give rise to such unusual pairs? And what other surprises are waiting to be uncovered? As we continue to detect more gravitational waves, the story of black holes is becoming richer and more complex. These ripples in spacetime aren't just revealing new objects, they're challenging our fundamental assumptions about the cosmos. And with every new discovery, we're reminded that the universe is full of mysteries waiting to be unraveled. Next, we'll explore how these gravitational wave detections are putting Einstein's theory of general relativity to the test, confirming its predictions while also hinting at places where it might need to be revised. Now, shifting our focus to one of the most profound implications of gravitational waves, let's explore how these cosmic ripples have not only confirmed Einstein's theory of general relativity, but also opened up new avenues to test its boundaries. When Einstein first proposed his theory over a century ago, he predicted that massive objects like black holes or neutron stars could create ripples in space-time gravitational waves. For decades, this remained a theoretical idea until the historic detection in 2015 proved him right. That moment wasn't just a triumph for science, it was a validation of one of the most elegant frameworks ever devised to explain the universe. But gravitational waves have done more than just confirm Einstein's predictions. They've given us a powerful tool to probe the limits of his theory. General relativity has been incredibly successful in explaining the behavior of massive objects and the structure of spacetime on large scales. However, there are still mysteries it doesn't fully address, such as what happens in the extreme environments near black hole singularities or how gravity behaves at the quantum level. Gravitational waves allow us to test these scenarios in ways that were previously impossible. For example, by analyzing the signals from black hole mergers, scientists can check whether the waves match the predictions of general relativity with incredible precision. So far, the theory has held up remarkably well, but every new detection brings the potential to uncover subtle deviations that could hint at new physics. One of the most exciting aspects of this research is the possibility of discovering where general relativity might break down. In the intense gravitational fields near merging black holes, for instance, the fabric of spacetime is stretched and warped to its limits. If there are any flaws or missing pieces in Einstein's theory, these extreme environments are where they're most likely to show up. gravitational wave observations are like a cosmic laboratory, allowing us to test the theory under conditions that are impossible to recreate on Earth. And while no significant deviations have been found yet, the search itself is pushing the boundaries of our understanding. What's more, gravitational waves are helping us explore the connection between general relativity and other fundamental forces like quantum mechanics. These two pillars of modern physics have yet to be unified, and gravitational waves could provide the clues we need to bridge the gap. For instance, some theories predict that spacetime might have a granular, quantum foam structure at the smallest scales, which could subtly alter the way gravitational waves propagate. Detecting such effects would revolutionize our understanding of the universe. As we continue to observe more gravitational wave events, each one adds another piece to the puzzle. They're not just confirming what we already know, they're challenging us to think bigger and dig deeper. Einstein's theory has stood the test of time, but gravitational waves are giving us the tools to explore its limits and perhaps uncover the next great breakthrough in physics. Next, we'll dive into how pulsars, the cosmic lighthouses of the universe, are playing a surprising role in the detection of gravitational waves, offering yet another way to listen to the whispers of spacetime. Now, let's turn our attention to an unexpected yet fascinating player in the hunt for gravitational waves: pulsars. These rapidly spinning neutron stars, often referred to as cosmic lighthouses, are not just remnants of massive stars, they're also incredibly precise natural detectors of gravitational waves. But how exactly do these spinning beacons help us listen to the whispers of spacetime? Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across the sky like a lighthouse, creating regular pulses of light that can be detected here on Earth. What makes pulsars so remarkable is their incredible stability. Some pulsars spin hundreds of times per second, and their pulses are so consistent that they rival the precision of atomic clocks. This stability is what makes them perfect tools for detecting gravitational waves. Here's how it works. When a gravitational wave passes through space, it subtly distorts the fabric of spacetime, stretching and squeezing it ever so slightly. This distortion affects the timing of the pulses we receive from pulsars. By carefully monitoring the arrival times of these pulses over years or even decades, scientists can detect tiny deviations caused by gravitational waves. It's like listening to a cosmic metronome and noticing when its rhythm is thrown off by the faintest ripple in spacetime. One of the most ambitious projects using pulsars for gravitational wave detection is the Pulsar Timing Array. This involves observing a network of pulsars spread across the galaxy. If a gravitational wave passes through, it will affect the timing of pulses from all these pulsars in a predictable pattern. By analyzing these patterns, researchers can not only detect gravitational waves, but also determine their source and properties. This method is particularly effective for detecting low-frequency gravitational waves, such as those produced by supermassive black hole binaries or even the remnants of the Big Bang. What's truly exciting is that pulsar timing arrays complement the work of ground-based detectors like LIGO and Virgo. While LIGO and Virgo are sensitive to high-frequency waves from events like black hole mergers, pulsar timing arrays can pick up the low-frequency hum of much larger cosmic events. Together, these methods give us a fuller picture of the gravitational wave spectrum, allowing us to explore the universe in ways we never could before. Pulsars, with their precise pulses and unwavering stability, are more than just cosmic curiosities. They're invaluable tools in our quest to understand the universe. By harnessing their natural precision, we're opening up a new window into the cosmos, one pulse at a time. Next, we'll explore how these gravitational waves come together to create a cosmic symphony, painting a vivid picture of the universe's most extreme events. Now, let's step into a grand cosmic concert where the universe itself becomes a stage for one of the most extraordinary performances imaginable. Picture this: every collision of black holes, every merger of neutron stars, and every ripple from the birth of the cosmos contributes to a vast, intricate symphony of gravitational waves. This isn't just noise, it's a harmonious soundtrack that tells the story of the universe's most extreme events. Each gravitational wave is like a unique note in this cosmic orchestra. When two black holes spiral together and merge, they produce a powerful crescendo, a burst of energy that reverberates through spacetime. Neutron star collisions, on the other hand, create a sharper, more intricate melody, often accompanied by flashes of light across the electromagnetic spectrum. Even the faintest whispers from the early universe, remnants of the Big Bang, add a deep, resonant hum to this celestial composition. What makes this symphony so remarkable is its complexity. Just as a musical piece is made up of countless instruments playing in harmony, the universe's gravitational wave symphony is composed of countless events, each with its own frequency, intensity, and rhythm. Some waves are short and sharp, like the crash of cymbals, while others are long and drawn out, like the deep tones of a bassoon. Together, they create a rich, layered soundscape that scientists are only beginning to decode. This cosmic symphony isn't just beautiful, it's also incredibly informative. By listening to these waves, we can learn about the objects that created them. The pitch and volume of each wave tell us about the masses and distances of the colliding objects, while the timing of the waves reveals how often these events occur. It's like having a cosmic Rosetta Stone, allowing us to translate the language of the universe into something we can understand. What's even more fascinating is that this symphony is constantly evolving. As new gravitational wave detectors come online and our technology improves, we're able to hear more of this cosmic music than ever before. Projects like LISA, the space-based observatory, will allow us to tune into lower frequencies, revealing the deep, resonant tones of supermassive black hole mergers and other colossal events. It's as if we're adding new instruments to our cosmic orchestra, enriching the music and deepening our understanding of the universe. So, the next time you think about the universe, imagine it not as a silent void, but as a vibrant, dynamic symphony. Each gravitational wave is a note, each collision a chord, and together they create a masterpiece that tells the story of everything that ever was, is, and will be. And as we continue to listen, we're not just observers, we're part of the audience, marveling at the beauty and complexity of the cosmic concert. Up next, we'll explore how gravitational waves might hold the key to unlocking the mysteries of dark matter, one of the universe's greatest enigmas. Now, let's turn our attention to one of the most mysterious players in the cosmic symphony, dark matter. While we can't see it directly, dark matter makes up about 85% of the universe's total mass, shaping galaxies and influencing the cosmos in profound ways. But here's the intriguing question: could dark matter also leave its mark on gravitational waves? Scientists are beginning to explore this possibility, and the answers could reshape our understanding of the universe. One theory suggests that dark matter might clump together to form exotic objects, such as dark matter stars or even dark matter black holes. If these objects exist, their collisions or interactions could produce gravitational waves, offering us a rare glimpse into the invisible world of dark matter. Imagine detecting a gravitational wave signal that doesn't match the usual patterns of black holes or neutron stars. It could be the first clue that dark matter is playing a role in the cosmic orchestra. Another fascinating idea is that dark matter particles themselves might interact in ways that generate gravitational waves. For instance, if dark matter particles collide or annihilate, they could release energy in the form of ripples in spacetime. While these waves would likely be incredibly faint, future detectors with even greater sensitivity might be able to pick them up, opening a new window into the hidden universe. What makes this connection so exciting is the potential to solve one of the biggest mysteries in modern physics. Dark matter has eluded direct detection for decades, but gravitational waves could provide an indirect way to study it. By analyzing the unique signatures of these waves, scientists might uncover clues about the nature of dark matter, whether it's made of particles, exotic objects, or something entirely unexpected. As we continue to listen to the universe's gravitational wave symphony, the role of dark matter remains a tantalizing puzzle. Each new detection brings us closer to understanding how this invisible force shapes the cosmos and whether it leaves its own subtle notes in the cosmic soundtrack. Up next, we'll dive into another speculative yet captivating idea: the possibility of white holes and their potential connection to gravitational waves. Could these theoretical objects be part of the universe's grand performance? Let's find out. Now, let's venture into one of the most speculative corners of the universe: white holes. While black holes are well known for their immense gravitational pull, white holes are their theoretical opposites. Imagine a black hole in reverse. Instead of pulling everything in, a white hole would expel matter and energy, never allowing anything to enter. But here's the twist: white holes have never been observed, and their existence remains one of the most intriguing mysteries in astrophysics. So, could white holes produce gravitational waves? The idea is as fascinating as it is speculative. If white holes exist, their formation or sudden bursts of energy could theoretically create ripples in spacetime. These waves would carry unique signatures, unlike anything we've detected from black holes or neutron stars. Imagine a gravitational wave signal that doesn't fit the usual patterns. It could be the first hint that white holes are more than just a mathematical curiosity. One theory suggests that white holes might be connected to black holes through wormholes, forming a cosmic tunnel between 2 points in spacetime. If such a connection exists, the interaction between a black hole and a white hole could generate gravitational waves, offering a glimpse into the hidden mechanics of the universe. While this remains purely theoretical, the possibility is enough to spark the imagination of scientists and enthusiasts alike. What makes white holes so captivating is their potential to challenge our understanding of physics. If they exist, they could provide insights into the nature of spacetime, the behavior of singularities, and even the origins of the universe itself. Each gravitational wave detection brings us closer to answering these questions, and the search for white holes adds an exciting layer of mystery to the cosmic symphony. As we continue to explore the universe's most extreme phenomena, white holes remind us that there's still so much we don't know. Their elusive nature keeps the door open for discovery, and who knows, the next gravitational wave signal might just hold the key to unraveling their secrets. Up next, we'll explore another theoretical wonder: wormholes, and their potential role in the universe's gravitational wave orchestra. Could these cosmic shortcuts be part of the grand performance? Let's dive in. Now, shifting our gaze to another cosmic enigma, let's explore the fascinating concept of wormholes. Often depicted in science fiction as shortcuts through space and time, wormholes are theoretical tunnels that could connect 2 distant points in the universe. But beyond their imaginative appeal, wormholes might also play a role in the universe's gravitational wave symphony. If they exist, the dynamics of these cosmic tunnels could produce gravitational waves with signatures unlike anything we've observed before. Imagine a wormhole as a bridge between 2 black holes, or even a black hole and a white hole. As matter or energy passes through this tunnel, the intense gravitational forces at play could create ripples in spacetime. These waves would carry unique patterns, offering clues about the structure and stability of the wormhole itself. Detecting such a signal would be groundbreaking, not only confirming the existence of wormholes but also revealing new insights into the fabric of the universe. One intriguing possibility is that wormholes could act as cosmic amplifiers for gravitational waves. If a wave passes through a wormhole, its energy might be magnified, creating a stronger signal that could be detected by instruments like LIGO. This amplification could help scientists identify wormholes indirectly, even if they remain invisible to traditional observation methods. It's a tantalizing idea that blends the boundaries of physics and imagination. Of course, wormholes remain purely theoretical for now, and their existence hinges on solving some of the biggest mysteries in physics, such as the nature of exotic matter and the stability of spacetime under extreme conditions. Yet, the potential for wormholes to produce gravitational waves keeps the door open for discovery. Each new detection brings us closer to understanding whether these cosmic shortcuts are more than just a figment of our imagination. As we continue to unravel the universe's secrets, wormholes remind us that the cosmos is full of surprises. Their potential to generate unique gravitational wave signatures adds another layer of intrigue to the cosmic symphony, inviting us to dream of what might lie beyond the limits of our current knowledge. Up next, we'll delve into how gravitational waves could shed light on one of the most profound questions in science, the existence of a multiverse. Could these ripples in spacetime hold the key to understanding parallel universes? Let's find out. Now, let's venture into one of the most mind-bending ideas in modern science, the multiverse. Could gravitational waves hold the key to proving or disproving the existence of parallel universes? This question takes us beyond the boundaries of our observable universe and into the realm of theoretical physics, where the multiverse hypothesis suggests that our universe might be just one of countless others. Gravitational waves, as ripples in space-time, carry information about the most extreme events in the cosmos. But what if these waves could also carry traces of interactions between universes? Some theories propose that if our universe collided with another in the distant past, the resulting gravitational waves might still be detectable today. These waves would carry unique signatures, unlike anything produced by black hole mergers or neutron star collisions, offering potential evidence of a multiverse. Another intriguing possibility is that gravitational waves could reveal the presence of branes, or multidimensional membranes predicted by string theory. In this framework, our universe might exist on one brane, while other universes exist on separate branes. If these branes ever collided or interacted, the resulting gravitational waves could leave behind a distinct imprint, detectable by advanced observatories. Such a discovery would revolutionize our understanding of reality, suggesting that our universe is just one layer in a vast cosmic tapestry. Of course, the multiverse remains a highly speculative idea, and detecting evidence for it through gravitational waves would require unprecedented precision and sensitivity. Yet, the mere possibility adds a thrilling philosophical dimension to the study of these cosmic ripples. It challenges us to consider whether our universe is unique or part of a grander, interconnected multiverse. As we continue to explore the universe's mysteries, gravitational waves offer a unique window into questions that stretch the limits of human imagination. Whether or not the multiverse exists, the search for answers reminds us of the boundless curiosity that drives science forward. Next, we'll turn our attention to another fascinating concept: cosmic strings, and how they might contribute to the universe's gravitational wave symphony. Stay tuned. Now, shifting our focus to another fascinating cosmic mystery, let's explore the role of cosmic strings in the universe's gravitational wave symphony. Cosmic strings are hypothetical one-dimensional objects, thought to be remnants of the early universe, formed during phase transitions just moments after the Big Bang. Imagine them as incredibly thin, ultra-dense threads stretching across the cosmos, thinner than an atom but with immense mass. If they exist, these cosmic strings could be among the most exotic and extreme objects in the universe. What makes cosmic strings so intriguing is their potential to produce gravitational waves. Unlike black holes or neutron stars, which generate waves through collisions or mergers, cosmic strings could create ripples in spacetime simply by vibrating or forming loops. These vibrations, caused by the immense tension within the strings, would send out gravitational waves with unique signatures, unlike anything we've detected so far. Detecting such waves could provide direct evidence for the existence of cosmic strings, offering a glimpse into the universe's earliest moments. The idea of cosmic strings also ties into broader theories about the universe's structure. Some models suggest that these strings could act as cosmic scaffolding, influencing the formation of galaxies and large-scale structures we see today. While they remain purely theoretical for now, the search for cosmic strings and their gravitational wave signatures is an exciting frontier in astrophysics. Advanced observatories like the Laser Interferometer Space Antenna, or LISA, could one day detect these elusive waves, opening a new window into the universe's origins. As we continue to unravel the mysteries of the cosmos, cosmic strings remind us of the profound connections between the universe's smallest scales and its largest structures. Whether they exist or not, the pursuit of these cosmic threads pushes the boundaries of our understanding, challenging us to think beyond the known and into the realm of the extraordinary. Next, we'll dive into another mind-bending concept, quantum foam, and how it might shape our understanding of spacetime itself. Stay tuned. Now, let's zoom in, way in, to the tiniest scales of the universe, where the fabric of spacetime itself becomes a chaotic, bubbling sea known as quantum foam. This mind-bending concept suggests that at the smallest possible distances, spacetime isn't smooth and continuous as we often imagine, but instead a frothy, turbulent mess. Picture it like the surface of a boiling pot of water, but on a scale so small it's almost impossible to comprehend. This quantum foam is thought to exist at the Planck scale, where the rules of quantum mechanics and gravity collide, creating a wild, unpredictable environment. So, how does this quantum foam connect to gravitational waves? Well, if spacetime is foamy at these minuscule scales, it could have a subtle but profound effect on how gravitational waves travel through the universe. Imagine a ripple moving across a choppy ocean instead of gliding smoothly. It might encounter tiny bumps and distortions along the way. In the same way, gravitational waves passing through quantum foam could experience slight fluctuations or distortions, altering their path or even their frequency. These effects would be incredibly small, but if we could detect them, they might reveal clues about the fundamental nature of spacetime itself. The idea of quantum foam also challenges our understanding of gravity and the universe's structure. It suggests that at the most fundamental level, spacetime might not be a fixed stage but a dynamic, ever-changing entity. This has implications for everything from black holes to the Big Bang, as it could reshape how we think about the origins and evolution of the cosmos. While quantum foam remains a theoretical concept, its potential influence on gravitational waves offers a tantalizing opportunity to explore the universe's deepest mysteries. As we push the boundaries of our knowledge, quantum foam reminds us that even the fabric of reality might be more complex and chaotic than we ever imagined. Next, we'll explore another fascinating idea, exotic matter, and how it could leave its mark on the gravitational wave symphony. Stay with us as we continue to unravel the universe's most extreme phenomena. Now, let's venture into the realm of the truly bizarre exotic matter. This isn't your everyday material. Exotic matter is a theoretical substance that defies the usual rules of physics. Unlike ordinary matter, which has positive mass and energy, exotic matter could possess negative mass or energy, bending the laws of nature as we know them. Imagine a substance that pushes instead of pulls, or that could theoretically warp spacetime in ways that seem straight out of science fiction. While exotic matter hasn't been observed yet, its existence could revolutionize our understanding of the universe, and gravitational waves might just be the key to detecting it. So, how could exotic matter leave its mark on gravitational waves? If exotic matter exists, it could create extreme distortions in spacetime, far beyond what we see with ordinary matter. For instance, exotic matter might form structures like wormholes or cosmic strings, which could produce unique gravitational wave signatures. These waves would carry the imprint of the exotic matter's unusual properties, potentially revealing its presence. Imagine detecting a gravitational wave that doesn't match the patterns we expect from black holes or neutron stars. It could be a sign that exotic matter is out there, reshaping the fabric of reality. The implications of exotic matter go beyond just gravitational waves. If it exists, it could help explain some of the universe's biggest mysteries, like dark energy or the nature of wormholes. It might even open the door to technologies that sound like pure fantasy, such as warp drives or time travel. While these ideas are still speculative, the possibility of detecting exotic matter through gravitational waves offers a thrilling glimpse into the unknown. It's a reminder that the universe is full of surprises waiting for us to uncover them. As we continue to explore the universe's most extreme phenomena, exotic matter stands as a tantalizing frontier. Its potential to produce unique gravitational wave signatures could one day provide the evidence we need to confirm its existence, or challenge our understanding of physics altogether. Up next, we'll dive into another mind-bending topic, the speculative connection between gravitational waves and time travel. Stay tuned as we unravel more of the universe's deepest secrets. Now, let's take a leap into the realm of science fiction, where gravitational waves might just hold the key to one of humanity's most tantalizing dreams, time travel. While the idea of traveling through time has long been a staple of movies and books, could gravitational waves offer a real-world connection to this fantastical concept? The answer lies in the strange and mind-bending nature of spacetime itself. Gravitational waves are ripples in spacetime, created by the most violent and energetic events in the universe. But what if these ripples could be manipulated or harnessed in some way? Some theories suggest that under extreme conditions, gravitational waves might create distortions in spacetime so intense that they could form closed time-like curves, a fancy way of saying loops in time. These loops could, in theory, allow for time travel, where an object or even information could travel back to its own past. Imagine a gravitational wave so powerful that it twists spacetime into a knot, creating a pathway through time itself. Of course, this is all highly speculative. The energy required to create such distortions would be beyond anything we can currently imagine, and the physics involved is still far from understood. But the idea isn't entirely without merit. Einstein's theory of general relativity, which predicts gravitational waves, also allows for the possibility of these closed time-like curves. While they've never been observed, their theoretical existence keeps the door open to the possibility that time travel might not be as impossible as it seems. What's even more intriguing is that gravitational waves could serve as a tool to test these ideas. If we were to detect a gravitational wave with unusual properties, perhaps one that doesn't match the patterns of black hole mergers or neutron star collisions, it could hint at something far stranger. Could it be evidence of a spacetime loop or a wormhole, both of which are often linked to time travel in theoretical physics? While we're not there yet, the study of gravitational waves continues to push the boundaries of what we think is possible. So, while time travel remains firmly in the realm of speculation, the connection to gravitational waves offers a fascinating avenue for exploration. It's a reminder that the universe is full of mysteries waiting to be unraveled, and who knows? One day, gravitational waves might just help us unlock the secrets of time itself. Up next, we'll explore another intriguing possibility: the role of advanced alien civilizations in detecting or even producing gravitational waves. Stay with us as we dive deeper into the cosmic unknown. Now, shifting our gaze beyond Earth, let's ponder an even more extraordinary idea. Could advanced alien civilizations be out there, not just detecting gravitational waves, but perhaps even producing them? It's a thought that stretches the boundaries of our imagination, but when it comes to the cosmos, the possibilities are as vast as the universe itself. Imagine a civilization far more advanced than ours, one that has mastered the intricacies of spacetime and harnessed the power of gravitational waves. Such a civilization might use these ripples in spacetime as a form of communication, sending signals across galaxies faster than light could ever travel. Gravitational waves, after all, are unaffected by the obstacles that block electromagnetic waves, like dust clouds or magnetic fields. This makes them an ideal medium for interstellar messaging, especially for a species that has unlocked the secrets of the universe. But it doesn't stop there. An advanced alien civilization might also manipulate gravitational waves for propulsion, creating distortions in spacetime to bend the fabric of the universe itself. This could allow them to traverse vast cosmic distances in ways we can barely comprehend. Think of it as a cosmic shortcut where spacetime is folded like a piece of paper, bringing distant stars and planets within reach. While this sounds like science fiction, the physics behind it is rooted in the same theories that predict gravitational waves. What's even more fascinating is the possibility that we might already be detecting signs of such civilizations without realizing it. Gravitational wave observatories like LIGO and Virgo are constantly listening to the universe, picking up signals from black hole mergers, neutron star collisions, and other cosmic events. But what if some of these signals don't fit the expected patterns? Could they be the fingerprints of alien technology hidden in plain sight? It's a tantalizing thought, and one that keeps scientists on the lookout for anomalies in the data. Of course, this is all speculative, but it's a reminder of how much we still have to learn about the universe. Gravitational waves have already revolutionized our understanding of the cosmos, and they might just hold the key to answering one of humanity's oldest questions: are we alone? As we continue to explore the mysteries of spacetime, who knows what we might discover, or who might discover us? Up next, we'll wrap up our journey with a celebration of human ingenuity and the incredible technology that has made gravitational wave detection possible. Stay tuned as we explore the final frontier of this cosmic adventure. Now, as we reach the final chapter of our cosmic journey, let's take a moment to marvel at the role of human ingenuity in unlocking the secrets of gravitational waves. It's a story of curiosity, perseverance, and the relentless pursuit of knowledge, a testament to what we can achieve when we dare to dream big. The detection of gravitational waves is nothing short of a technological triumph. Think about it. We've built instruments so sensitive they can measure distortions in spacetime smaller than a fraction of an atomic nucleus. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is a prime example of this engineering marvel. Its massive arms, stretching over 2.5 miles, are designed to detect the faintest ripples in spacetime caused by events billions of light years away. And it's not just LIGO. Collaborations with observatories like Virgo in Europe and Kagra in Japan have created a global network of detectors working together to listen to the universe's whispers. But the story doesn't end with the hardware. Behind every gravitational wave detection is a team of brilliant minds: physicists, engineers, mathematicians, and computer scientists who have spent decades refining theories, analyzing data, and solving problems that seemed insurmountable. Their work has not only confirmed Einstein's century-old predictions, but also opened a new window into the cosmos, allowing us to observe the universe in ways we never thought possible. What's truly inspiring is how this achievement reflects the best of humanity. It's a reminder that, despite our differences, we can come together to tackle the biggest questions about our existence. From the first glimmer of an idea to the groundbreaking discoveries of today, the journey of gravitational wave science is a celebration of collaboration, innovation, and the unyielding spirit of exploration. As we close this chapter, let's not forget that this is just the beginning. With projects like the Laser Interferometer Space Antenna, or LISA, on the horizon, we're poised to take gravitational wave astronomy to even greater heights. Who knows what mysteries we'll uncover next? One thing is certain: as long as we continue to push the boundaries of what's possible, the universe will keep surprising us. And with that, we wrap up our exploration of the universe's most extreme gravitational waves. If you've enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss out on our next adventure into the wonders of space. Until next time, keep looking up. The universe has so much more to reveal. As we bring our cosmic journey to a close, let's take a moment to reflect on the incredible story of gravitational waves. From the first detection in 2015 to the mind-bending discoveries of black hole mergers, neutron star collisions, and the echoes of the Big Bang, we've explored 30 awe-inspiring facts that reveal just how extraordinary these ripples in spacetime truly are. Gravitational waves have not only confirmed Einstein's predictions but have also given us a new way to listen to the universe, uncovering secrets that were once beyond our reach. These waves are more than just scientific curiosities. They're a testament to the power of human curiosity and innovation. They've shown us the universe in a way we've never seen before, from the violent collisions of black holes to the delicate spirals of neutron stars. Each detection has brought us closer to understanding the cosmos, revealing its most extreme and mysterious events. And with projects like the Laser Interferometer Space Antenna on the horizon, the future of gravitational wave astronomy promises even more groundbreaking discoveries. But this is just the beginning. The universe is vast and there's so much more to explore. If you've enjoyed this journey through the wonders of gravitational waves, don't stop here. Dive deeper into the mysteries of space, science, and the cosmos. And if you want to stay updated on our next adventures, make sure to hit that subscribe button, ring the notification bell, and join us as we continue to uncover the secrets of the universe. Until next time, keep looking up. The cosmos is full of surprises, and we can't wait to share them